So good morning all, and it's a great pleasure to have Professor Venkatesh here from IISc, who will be lecturing us on the universal enveloping algebras and the related stuff. So please welcome Professor Venkatesh, and I request him to start.
Yeah, thank you very much. So I am audible, no? There is no issue, no?
Yes, you are audible.
Okay. So I will be actually lecturing on the universal enveloping algebra and some results related to that. So I have been given 3 lectures. So the very first lecture I will focus on introducing what is universal enveloping algebra, and we will actually see some of the basic properties of that. And then if time permits, actually I will try to at least give statement of PBW theorem and some equivalent versions of that. And later, so in the second lecture, we will try to actually complete the proof of PBW theorem. So later we will use PBW theorem and then try to understand Sear's presentation of semi-simple Lie algebras. So I assume like all of you must have gone through some background in Lie algebras. Okay, so
there were 2 lecture series before yours. Yeah, so they have seen Shraddha's introductory lectures and Sachin's lectures on root systems.
Okay, great.
And I have also, sorry to interrupt again, but I have also shared your file. Yeah, the notes that you shared with me. I have uploaded them in the folder for everybody, and I have also shared it in this chat.
Okay. So basically, the lecture notes that I shared was written by Anne Moore. So she actually kind of gives kind of quick introduction to the things without getting into too much details. But again, like there are some typos, so one should be careful with reading that file. So for this PBW theorem proof part, mostly I will be following the book of Roger Carter. So anyway, like in this lecture, let us actually start with some universal constructions and then get into the definition of universal enveloping algebra. Okay, so this is more like a recall. So whatever stuff you are expected to study in first course in algebra or second course in algebra, so I will be just recalling it. So let's start with something very basic. So we will define what is called tensor algebra. So let's start with any vector space. So I will always work with complex numbers. Okay. So our ground field. Sorry. So our base field, we will always stick with complex numbers. So now let's start with the vector space V. Okay, it's V be a vector space over C. So then we want to define what is called tensor algebra of this V. So first let's actually kind of consider this k-fold tensor products. So let's call this as T power kV. So this is tensor products of k copies of V, where this number of V appears k times. So now what we do, we take this direct sum of all this TKV, so that we denote it by T. So this is the direct sum of TKV where k greater than or equal to 0. So now it's easy to see that, or by convention, actually, we want to have when k equal to 0, so T0V to be our complex numbers, and T1V by definition is just V. Okay. Similarly, T2V, which will be interesting for us, this is two full tensors, V tensor. So now we have a natural product on this on the space T of V. So that is actually given by what is called this juxtaposition. So you take M full tensor and then N full tensor. Okay, let's actually write it. So X1 tensor, etc. Xm, and then you take Y1 tensor, etc. Yn. So this is M fold and N fold tensor. So the product between these two defined to be actually just writing them in one line. So this is called just to the juxtaposition. So you write x1 tensor, etc. xm tensor, y1 tensor, etc. tensor y. So this actually defines multiplication on this linear space T of V. So that makes it T of V an associative algebra, so which is called a tensor algebra of V. So this T of V, an associative algebra. Okay, and this is also called what is called tensor algebra of this capital. So now note that so this complex numbers is identified with the T0V. So in particular, there is 1 inside this T0V. So this is indeed the identity element. So this is identity with respect to the multiplication. So this actually kind of gives you, this makes it actually this T of A as unital C associative algebra. Okay, so this is also unital C associative algebra. Okay, so this is actually kind of a very abstract definition of the tensor product. So of course, so what will be doing in this lecture actually, so I will try to actually parallelly go through the abstract definitions of all these universal constructions like tensor product, symmetric algebra, universal unique algebra, and so on. But I will also tell you like how to work with them in a more practical way. Okay, so with that note, like let us actually see what this tensor product means in more practical sense. So that's what more important to us. So if I actually, so mostly like we will be considering only 5-dimensional algebras. So that's why we can actually just assume our space to be 5-dimensional. But again, everything actually works for any infinite dimensional algebras, so infinite dimensional spaces. So if I take, for example, okay, let's fix this V and then fix a basis of this V. So let's use this notation. So I will use this capital letters whenever I'm actually working with this associative non-commutative algebra. So capital X1, etc., Xn. So this is the basis of, let's say, V. Okay. So if you think about the tensor product, so which is a very abstract notion, but indeed what we are considering, so the tensor products of various elements that comes from V. So if you use in terms of, if you rewrite everything in terms of this basis elements, then all you are actually doing is you are looking at words that are formed using these letters x1, etc., xn, and then you are taking linear combinations of that. So what I'm trying to say, for example, if you take some typical basis element of the tensor product, so which will look like xi1 tensor, etc., tensor xik. So it is a fact, maybe you should do it as exercise. So if you run over all possible these kind of tensors, xi1, etc., xik, where these i1, etc., ik, let's say they are some indices that come from this 1 to n. Okay, so they are not ordered, so it could be in any order, and then only thing is they should come from this 1 to n because we have fixed the basis of v to be x1, etc., xn. So if you take all possible words like this, okay, so this is something I would like to think it as a word. So what I would do, I would actually stop dropping this tensor. So instead of writing this as xi1 tensor xik, I would write this as just as a word like xi1 etc. xik. For example, if you take the word 3, 2, 1, let's say 4, then we are considering x3, x2, x1, and x4. So this is the word that we are actually considering associated with this notation. So now what we are doing, we are taking all possible words so that you can form using this alphabets x1, etc., xn. And so that is indeed like parameterizing set for basis of this tensor product. So it's just another way of writing the basis. Now, if you take all possible C-linear combination of those words, then you are actually getting the tensor product. Okay, so the T of V is so all possible linear combination of this word. So the span of C over, so let's call this as B. Okay, so this is actually somewhat combinatorial way of thinking about tensor product. But if you actually think more closely, so this is actually naturally isomorphic to there is a notion of free non-commutative associative algebra generated by this x1 etc. xn. So we are not imposing any relations, okay, polynomial relations in xi, and then we don't want those xi's to commute. So you are taking all possible words out of this exercise, and then you are actually taking possible linear combination. So that actually gives you what is called free, okay, associative algebra. So this is also non-commutative. So C algebra, C associative algebra generated by these symbols x1, etc. So that's what you are getting as tensor product. So now let us actually write down the universal property of this tensor product. So if you actually look at this tensor product, which is freely generated by this xi's over this complex numbers, so it's easy to see this has this following universal property. So which like again I will leave it as exercise. So one needs to actually know this kind of you defining these objects using these universal properties. So this, for example, like definition also can be carried to all other objects. So what it is, so indeed what we did actually existence of such an object. So now we are going to actually define it using this universal property. So let's actually write it in terms of diagram. So let's start with this V, and let's say you have a C-linear map from V to, let's say, some associative algebra A. So this A is given to be a unital associative K algebra, sorry, C algebra. So then what you have like, so you already have a natural map from V to this T of V by taking V to T1 of V. Okay, so this there is this natural map from T to T on V, and then that's actually sits inside TV. So this is the map that we are talking about here. Let's call it iota. So then given this linear map, let's call it pi. So there exists unique extension of this pi from T of V to A. So there exists unique extension pi tilde of this pi from T of V to A, such that this diagram commutes. So whenever I say there is unique extension of pi, that means already in terms of the diagram, this diagram commutes. Okay. So this universal property is true for tensor algebra. So this is one way of defining, but again, like this doesn't say the existence, but the construction very explicitly say such algebra exists. Okay, so now let's actually look at the commutative version of this. So if we take the variables x1, etc., xn, and then if we allow them all to commute, then let's see what happens. Okay, so v you have, and then you have this basis, so which is denoted by x1, etc., xn. So now we know that in the tensor algebra, these x's don't commute. But what if you allow all of them to commute? Let's see what happens. So because we want them to commute, so the one way to do this, you take this free non-associative, sorry, non-commutative algebra. And then what you can do, you can take, so you want them to commute, you take the two-sided ideal generated by this xi, xj minus xj, xi. Okay, so that will do the job. So basically what we are doing, so let's take this I, so which is the two-sided ideal generated by, so you can just simply take it on the basis, or otherwise you can also allow all possible linear combinations. So you can actually simply take it to be like x tensor y minus y tensor x, where xy comes from capital V. Okay, so then if you take this ideal and then go modulo this ideal, so that means you are taking the tensor algebra going modulo this ideal. So that is what is called the symmetric algebra of V, so which we denote it by S of V. So this we call it the symmetric algebra. Okay, generated by. So now it's easy to see that because you are going modulo these relations. So when you actually take this image of xi to be, let's call it small xy. So whenever I write small xy, that means I'm actually using for this lecture. So I'm assuming those small xi to commute. Okay. So you have this natural map from T of V to S of V, which is the quotient map. So then if you call this image of capital Xi to be small xi, then it is clear that the small xi's, they commute, okay, for all h. So that means what you are getting at the end is actually the polynomial algebra generated by these variables xi. So you are getting the polynomial algebra on this xi. Okay. So again, you can use the universal property to define the same object. So again, I will leave it as exercise. This is not very hard. So now, so you have the same picture. So there is this V. So V is indeed sitting inside this T of V, and then you have this quotient map from T of V to S of V. So this is iota and this is pi. So now note that T of V is actually naturally graded. So you can use the total degree of these monomials that appear in the basis, and then you can actually use that ordering to order the elements of T of V. In particularly, T of V is graded algebra. Okay. So the grading also already specified in the very beginning, so which is exactly the direct sum of that tk of v k greater than or equal to 0. So this is indeed the total degree of the monomials. Okay, that comes from this. So this comes from the total degree of the monomers. Okay, so now you have this graded algebra. So what does it mean? So whenever you take tk of v times tk dash of v, so then that should be inside tk plus k dash of v. So that is satisfied. Okay. So now what's about the ideal that we actually defined before to define this S of v? So if you actually consider that ideal, so this ideal is two-sided ideal generated by x tensor y minus y tensor x, where xy comes from e. So now note that the degree of these terms, so they both are 2. So this has degree 2 and this also has degree 2. So that means this ideal is actually graded ideal. So this ideal is indeed graded ideal. So that means if you go modulo this ideal, so then you get again the graded algebra. So this is again graded algebra. So in particularly what you have, so this I will leave it as again exercise. This is not very hard. If you take I and then you can write it as just direct sum of T mv intersection I, where m greater than or equal to 0. And note that, so it's not very hard to see because the generators have degree 2. So if you take a two-sided ideal generated by that, so all the elements that appear in I, if you, the homogeneous part of that, all of them should have at least degree 2. So in particularly T0V intersection I should be trivial, and again T1V intersection I also will be trivial. So in particularly, you can see that C sits inside S of V, so which can be identified with S0 of V, and similarly S1 of V can be identified with V. Okay. So now, if you go back to like, sorry. We go previous page. Yeah. So now we are looking at this map. And we want to actually write down the universal property of this S of V in terms of this map. Okay, so this composition is indeed injective. Okay, so let's write down that injective map. As again, we will denote it by iota. So now using this map, if we the universal property, so I will leave it as exercise again. So you have the same diagram. So instead of TV, you have S of V, and then here again A, but this is given linear map from V to A, but now A should be unital commutative C algebra. So this is supposed to be unital commutative C algebra. Okay, so that is the only difference between the tensor algebra and the symmetric algebra. So now given given this linear map pi, so this is supposed to be just a C linear map. So one way to remember, just to remember the structure that possesses these objects. So then it will be clear what will be the natural condition that you need to write down for the maps. Okay, and here you have this iota, which is also linear map. So then there exists unique extension pi tilde of this pi. And now this pi tilde, that is supposed to be C algebra map. Okay, this is C algebra homomorphism. So like such that this diagram commutes. Okay, so this is the universal property for the symmetric algebra. Okay, so now let us look at some interesting examples so that actually kind of lies between these two. So one actually kind of think about, okay, so tensor algebra is indeed none of the variables xi commutes, but when you come down to S of v, then all the variables xi they commute. But then so between these two, you can actually kind of sandwich some algebras. Okay, so they are called what's called partially commutative C algebras. So you can actually have what is called partially commutative C algebras. Okay, again they are free partially commutative, because so what we are going to do, so how they are defined, so they are defined by, okay, they are defined by declaring only some of the variables to commute, only some of the variables xi to commute. Okay, so one very good way of actually keeping track of which variables to commute, you can take a matrix, n by n matrix, and then you just to put entry 0 or 1, okay, depending upon whether those two actually variables xi xj commutes. Okay, again you have to take the symmetric matrix to be consistent. Another way of representing the same data, you can actually define a simple graph on this 1 to n vertices, and then you put an edge whenever the variable xi xj don't commute, and then whenever they commute, you just don't put edge. Okay, so you can record this data using either matrix or the graph. But it's very clear that so one way of actually defining as before, so you can start with this tensor algebra. To define this free partially commutative C algebra, what you do, you take the two-sided ideal generated by those variable for which you want them to commute, okay, and then you go modulo that. Then you will be getting this free partially commutative algebra. So let me just write down the definition. So this is kind of one set of examples that you should actually always remember. Okay, so you have this tensor algebra. Okay, let's say the graph is given. So this is a simple graph on the vertices 1 to n. Okay, basically the same as x1 except xn. So now what you do, like you are defining this this partially commutative C algebra. Okay, free partially commutative algebra. So associated with G. So you take this TV, then go modulo two-sided ideal generated by this xi xj minus xj xi. So whenever there is no edge between I and J. Okay, so this is the ideal that we are actually going model. So then what you get this free partially commutative algebra. Okay, so we will also see the corresponding Lie algebra version later, but anyway, let's move on. Okay, so now, so let me actually tell you one general construction. So all of these algebras that we are actually considered before, they are all graded C algebras. But then you can ask this question, how to generate graded algebras in general. Okay, so there are two ways actually one can construct graded algebras. Okay, so this is the machinery. So how to get graded algebras. So you can follow these two procedures. So first procedure we already seen. So this is actually going modulo actually graded ideals. Okay, you go modulo. Oh, sorry, deleted everything. So first procedure is okay, go modulo graded ideals. So you start with graded algebra. Okay, start with graded algebra, and then take graded ideals, and then you just go modulo that. Then what you get is indeed graded algebra. The second procedure, so you can actually start with what is called filtered algebra. Okay, so you can start with filtered algebra. So again, all algebras are actually, we are considering over complex numbers. So all this general notion can be defined over even general commutative rings and so on. So we are not going to consider in that generality, we will work over only complex numbers. So you can start with filtered algebra, and there is a procedure called like just you can start the filter algebra, you can consider the graded algebra associated with that. So using that procedure, you can actually produce graded algebra. Okay, so you can actually define the graded algebra again associated with this given this year. Okay, so this procedure is very important. Like, let's see like how one does that actually. So before that, let's actually define what is filtered algebra, and then we'll proceed. Again, we are going to only consider filtration over Z plus. So let's use this notation Z plus. So these are all like just not like all these non-negative integers. Okay, so this is set of all non-negative integers. So that means it includes 0. So that's important. Okay, so we are going to consider filtered algebra which has filtration over Z plus. So what it is, so A is called filtered algebra. Then you have this filtration, so which is sequence AI in Z plus. So such that okay, A is union of AI, and you need to have this filtration. The filtration is given by like A0 is contained in A1, A1 contained in A2, and so on. Okay, so this is called filtration. And A is called filtered algebra if there is some filtration. Okay, so now using this data, how you can actually construct this graded algebra associated with this. So let's actually look at it. So what you can do, okay, sorry, the filtration actually kind of not only it has this increase in chain. So because the algebra thing should be reflected. So whenever you take the product from AI and then AJ, that should be contained in AI plus J. So this is where the algebra part is reflected. Okay, so these two conditions should be satisfied. So now, if you start with filtered algebra, so now how you can associate first of all graded space. So let's see, you take this.
So can you show the last slide once?
Sorry. So I will write it again here. Yeah. So you have this A, which is a filtered algebra. So this A can be written as union of AI I from 0 to infinity. So like I said, we are only considering the filtration like this, which is indexed over Z plus. So now you have this filtration, which is like subspaces of A such that which is increasing with respect to the containment. And this also should satisfy this condition. AI times AJ should be contained in AI plus J. So note that all these AIs are all C subspaces, okay? So they are not just random subsets, so they are C subspaces such that all these things are happening. So mostly like I will not specify the linear structure, okay? So all the things that we are going to consider will have linear structure. Okay, so now how are you going to get this graded associated space? So which is defined as follows. So all you do is just it's denoted by grade of A. So this is defined to be you take the direct sum of all these quotient spaces. You take AI, go modulo AI minus 1, where I is very marginal from T. Okay, so this is my graded associated space. Okay. So it's easy to see that this carries all the C vector space structure, so that is not a problem. But we need to have the algebra structure. So we need to actually define product. So the product is naturally defined. Okay. So whenever you take AI modulo AI minus 1 and then AJ modulo AJ minus 1. So with this two elements, so then you need to associate element in grade A. But because we are expecting it to have the graded structure, so naturally, so this AI minus AI modulo AI minus 1 will be the ith graded space. So this has to go end in AI plus J modulo AI plus J minus 1. Okay. So now, what is the definition? Okay. You take, for example, AI plus AI minus 1. So this is in AI modulo AI minus 1. And then you define the product between this and AJ plus AJ minus 1 to be the natural product that you see in algebra, AI, AJ. But then you go modulo AI plus J minus 1. Okay. So this is the product that you define. Now, it's easy to verify this is indeed well defined. Okay, so this is the important checking. So verify. So this is indeed well defined. So indeed, actually, when you take two different representatives, then you have to say that you will end up actually same image modulo this A I plus J minus 1. So it's easy to verify. Actually, let me do it in one line. So if you change the representative, you change it like this: AI plus some U I minus 1. Okay, and then AJ plus some again some V uj minus 1. Okay, the product, this is what you have to consider. Then if you take the product, you get AI AJ plus ui minus 1 AJ plus AI uj minus 1 plus ui minus 1 uj minus 1. So this is how you get the product. But then note that, so this element has grading I plus j minus 1. So maximum, that is what it will have. So this one has I plus again j minus 1, and this one has I plus j minus 2. So if you go modulo, like if you take modulo this I plus j minus 1, then you can see that this one and this one has same image. Okay, so that actually proves this is well defined. So once you prove this is well defined, then everything else will just follow. Okay. So now it's easy to see that this 1 is there in this A naught. So indeed A minus 1, I can take it to be 0. So the 1 that you have, that is already behaves like unital. So the one that is A will be having the image in grade A. So that makes it this grade A as unital, actually unital associative algebra. If you start with unital algebra. So if you start with A, which is filtered algebra, has unit, then the grade A will also have unit. That's what I think. Okay. So when this graded algebra will be commutative, Okay, it is very simple exercise. So the graded algebra is commutative if and only if whenever you take this AI from capital AI and AJ from capital AJ, so whenever you take a product of them or consider the commutator, that should lie in the smaller graded piece. Okay, so this grade A is commutative if and only if for any IJ, whenever you take AI in AI, AJ in, let's say, AJ, you know that AI times AJ will lie inside I plus J. But then if you want it to be commutative, then look at the commutator, AI AJ, which is AIJ, AI AJ minus AJ AI. So this should lie inside this AI plus J minus 1. Okay, so whenever you consider this commutator, that should lie inside the lower filtered space. So then it's guaranteed that whenever you take the corresponding product in the graded algebra, the grade of A, then that must be commutative. Okay, so this is something easy to see. And whenever in this graded world, you can also define actually morphism between the graded algebras. So now, if you have actually morphism between the filtered algebras, then that will actually induce morphism between these graded algebras. So what is the meaning of morphism between filtered algebras? Let's take A and B to be given filtered C algebra. So that means there is some filtration. Okay. Again, let's assume for simplicity, A naught is C and B naught is C. They are isomorphic to C. Okay. So now you have a, let's say, C linear map from A to B. So this is a C linear map, and you want this to be actually morphism of filtered algebras. So that means it must be, first of all, C algebra homomorphism. So this is a C algebra homomorphism, and we also need to have this filtration should be preserved. Okay, whenever you take f of AI, that should be mapped inside BI. Okay, so A comes with filtration AI, B comes with filtration BI. Then filtered algebra homomorphism is a C algebra homomorphism that actually preserves the filtration. So now it's an easy exercise. If you have such morphism, then that will actually induce C algebra map from the graded associated algebra. Okay, so you can define the grade F. Okay, that is from grade A to grade B. So which is a natural map. So which is defined to be the grade F of AI plus AI minus 1 is given to be F of AI plus BI minus 1. Okay, and this map is indeed map between the graded algebras. Okay, that means a C algebra map, and that also maps the ith grid space to ith grid space. Okay, so verify grade F is C algebra graded homomorphs. Okay, so these are all something easy to verify. Okay, so let's actually like come back to the topic that I'm supposed to lecture. So all these things are some background about understanding this the object that we are interested in. So the object that we are interested in is what universal enveloping algebra. Okay, because these universal enveloping algebras, they are very important in order to understand the representation theory of these Lie algebras. So let me actually first motivate so where they come from, and then we will see some of the basic properties of them. Okay, so here is the setting. So let's say we start with this Lie algebra G. Okay, so we know that most of these Lie algebras, they appear as linear subalgebras. Okay. So that is why it's natural to expect some associative algebra is sitting above this given Lie algebra. So let me use this G for Lie algebra. Okay. So it is abstractly given Lie algebra. Suppose if this G sits inside, let's say, some GL of V, so then you have a natural associative algebra that can be associated with this G. Okay, so because this GL of V is indeed endomorphism of V, so this is indeed associative algebra. Okay, but this associative algebra, you are thinking it as a Lie algebra using the commutator bracket. So now, if we take this Lie algebra, so that is sitting inside this GL of V, then naturally you can actually look at the subalgebra generated by this G. Okay, associative C subalgebra generated by this G. So this is already there, sitting just above G. Okay, so in some sense, that is your enveloping algebra. Okay, not some sense, that is actually your enveloping algebra. Why you are interested in such algebra? Okay, you are interested in understanding the Lie algebra structure of G. Okay, more or less that is actually kind of reflected in this associative structure. Okay, so okay, just to motivate, let me not get into that relations between. Okay, one can actually study naturally. Okay, how the Lie algebra structure of G is reflected to this associative algebra that you have just constructed. Okay, it's actually a very nice question. So this question was actually answered very first by Hestin. Okay, in his old papers. For example, if you start with this, so he actually considers much more general setting. Okay, so he works over general rings and so on. So if your G is a simple Lie ring, okay, so let's actually write down the Heston result. So this is only the one way. Okay, maybe the example will be if you start with, for example, GLN, okay, so which is nothing but Mn of C. So this is as an algebra, C algebra. So this is actually a simple associative algebra. Okay, so this is simple associative algebra. So then if you consider the bracket, so which is SLN, okay, so basically Heston says the simple structure of this associative algebra is what gives you simple structure for this Lie algebra. Okay, of course he formulates this in the very general setup and then actually understands this. And like the converse is also somewhat you can understand using density theorem. So maybe like I'll formulate this later and then add it in the problem sheet. But here, without getting into this understanding the algebra structure, if you are only purely interested in, let's say, representation theory, then let's see this how this enveloping algebra is indeed helps. So let us fix one representation of G. Okay, so let's start with V being now just abstract Lie algebra, and then V is representation of G. Okay, so then by definition, it is actually a map from G to GL of V. Okay, and this is Lie algebra homomorphism. So now look at this pi of G. So pi of G is indeed a Lie subalgebra of this GL of V. Now what you can do, you can actually take this associative algebra generated by this pi of G. So this is the associative algebra generated by this pi of G. Now you can easily see that as long as this representation concerned, okay, only V is concerned, then it's a easy observation. Okay, let me state it as exercise. You take any W, if it is G invariant, then if and only if, so G invariant means it is a G submodule. Okay, so then W is obviously pi of G invariant, and obviously that is same as saying W is the subalgebra generated by that invariant. Okay, so basically what is the advantage of going from here to here? Okay, so the thing is you have G, so you have commutator, you know how to actually take the difference between two operators. So each element of G acts as an operator. Okay, so given X in G, this X is acting on this capital V. Then given Y also acts there. So but the commutator acts, that we know. But then there is no way to compose those. Okay, as maps you can compose, but there is no meaning of the product xy in G. Okay, so the product xy doesn't make sense inside your G. So in some sense, if the product makes sense, then your life will be easier. Okay, so let's say, okay, it doesn't make sense in G, but again, like somewhere, at least as long as the representation concerned, that makes sense when you go to that particular space. Okay, there is no issue. But then you can ask this question, okay, whether this can be done simultaneously for all representations of G. If you pick one representation, then you have this associative algebra naturally defined for G, and then all information about the representation in a way encoded using this associative algebra. For example, if V is irreducible, then it will be irreducible there. V is reducible, it will be reducible there, like indecomposable. All the notions that you know about basic representation, so all those notions will carry to G G representation to this enveloping algebra representation, which is generated by this pi of G. Okay, associative algebra generated by pi of G. But this is something like you are fixing one representation and then you are asking this question. But now can you vary like all possible representations and then do it this universally? So that is where this universal enveloping algebra comes in. So basically what you are interested in. So the question is, can you make sense of product of elements of G? Why you are interested in the product of elements? Because when you consider the representation of G, so you are like each element of G acts on the representation. So naturally the composition of those maps makes sense. Okay, when you have product, then you can expect that product also acts as composition of those. Okay, that is why you are actually getting into this product. Now, how one can make sense? Okay, so if you actually think about it, so G possesses first of all linear structure. So this is to begin with C linear structure. So this is a C linear space, and of course satisfying some additional condition that actually makes it Lie algebra. So then if you go with this C linear space, then there is this notion of TG, which is the tensor algebra that actually gives product of elements. Okay, but then if you work with TG, that TG looks actually much bigger than what you are actually expecting. Okay, why? Because so when you go from G to TG, the product of elements makes sense. There is no issue. But then if you think about it, okay, so if I take xy in G, and then if I look at this bracket xy, okay, which is actually a commutator of xy. So as an abstract product, this will be again element of G. But if you think how the xy actually acts on given representation, then this bracket xy, you are expecting it to be compositional, okay, the commutator of the respective maps. So it must be xy minus yx, okay. So this is supposed to be xy minus yx in some sense, whenever it acts on representation. But then you see this side, you have like degree 1 term in some sense, which is element of G, okay. And this side you have degree 2 term. So some kind of compatibility is not there, okay. And somehow like if you are working inside TG, then you can see that this xy minus yx, which is inside only degree 2, which will never reach to degree 1, okay. But how can I actually rectify this? So the best way of rectifying, so this is the demand that we are going to make, because whenever it acts on representation, you are expecting this to happen. Okay, the composition of xy minus yx should be coming from the image of bracket xy. So that is something expected. So what do? You just go modulo that. Okay, so that is the best way. So instead of taking TG, you construct TG and then modulo some ideal, and that actually gives you this. Okay, so what you do naturally. So let's call it J. You take two-sided ideal. Generated by x, y. Okay, so let's not use. Let's keep the tensor product. X tensor y minus y tensor x. But this x tensor y minus y tensor x, you want this to be matching with xy. So you just subtract that xy. And you do it for all elements of G. Okay. So now if you take this TG and then you go modulo this J, okay, inside this, if you take x plus j and then y plus j, then you can easily see that the bracket is same as x plus j times y plus j minus y plus j times x plus j. Okay, this identification is happening. And this space, you call it the universal enveloping algebra. Okay, so this is called the universal enveloping algebra. And this is actually we defined by explicit construction, and one can also define it using the universal property. And before that, let's actually observe something about this algebra. Okay, so first of all, the ideal that we have defined, so that is indeed not graded ideal. Okay, so this is not graded. Okay, so why? Because these two terms lie in degree 2, and this is supposed to be element of G, so this is inside degree 1. Okay, so obviously this is not graded relation, so this is not graded algebra. But then it's not difficult to see that J intersection T0V, okay, T0G is indeed trivial. Okay, because everything is actually like generated from combination of degree 2 and 1. So if you take anything generated from this, you will never reach degree 0. So that actually tells you that at least the scalars, which is identified with the T0 of V, survives inside your UG. Okay. Now, there is this natural filtration that you have on this tensor algebra. Okay, so recall tensor algebra is indeed graded algebra. So this is given by this Tm of V, m greater than or equal to 0. So this is indeed graded algebra. So using this grading, you can also easily create a filtered algebra. So let's see. So you can actually take Tm of G to be the direct sum of Tk of G, where K is up to M. Okay, then it's easy to see that T0 of G gives you the filtration on your tensor algebra. Okay, so indeed, the tensor algebra is filtered algebra, and it is not hard to see that quotient of filtered algebra will be filtered. Okay, so this is an exercise. So quotient of a filtered algebra is again filtered. So basically, filtration is actually comes from the filtration that you have started with. Okay, let's say pi is a map from A to B, and this A has filtration union AI. So then if this is actually surjective map, so then you can take Bi to be pi of A. So that then it's clear that union Bi is B, and it will satisfy all other required property. Okay. So because of that, you can easily see that the universal univariate algebra must be actually filtered algebra. So UG is indeed filtered CLG. Okay. So let's call this UM of G to be the image of this TMF. So let's call this pi as the quotient map from TG to UG. So this is the surjective quotient map. Okay, so you have these various maps. So if you think about it, so you have from G to TG, you have this iota, and then TG to UG, you have this surjective map. But note that, so here is the warning. So a priori, this composition need not be surjective. Okay, so let's look at this composition. Again, we call it iota. So this iota, okay, to begin with, need not be surjective, and it is actually consequence of PBW theorem. Okay, so the PBW theorem asserts that this map is indeed injective. Okay, so we will prove this later. Okay, so we have defined the universal enveloping algebra. Now let me actually verify the universal property of this universal enveloping algebra. So, and it's not very hard. Okay, so we have this G. Again, this is Lie algebra over C. So you can actually take it to be any Lie algebra. There is no issue. So there is no restriction on the dimension or anything. Now you have this picture. So you have G, and then you have UG, and then you have this iota. So we know that such a map is there. Okay, from G to TG you have map, and then from TG to UG you have quotient map. Then that is the composition that you are taking, G to UG. So now this is the setting given. Now, sorry, I couldn't hear. Am I audible?
Yes, you are audible. Please go ahead.
Okay. So if you start with this setup, okay, so let's actually look at what we had before. So you had V, TV, and then you had this associative algebra here. So the universal property of this was given pi, you had extension here, such that this diagram connotes. So very similar to that, you can actually start with A here, which is now, because UG being just associative algebra, you just demand this A to be unital associative algebra. Okay, so this is just unital C associative algebra. Now given any, okay, given now this pi, what is this pi? Okay, like I said, so depending upon the objects that are there, you need to decide the morphisms. Okay, that is one way to actually remember things. But here, this G actually, sorry, this V didn't have any structure. It had only C linear structure. But note that here G has both C linear structure as well as Lie algebra structure. So we expect this pi to be at least Lie algebra homomorphism. Okay, so this you expect this to be homomorphism. Then given this pi Lie algebra homomorphism, then you can prove that there exists extension of this pi such that this diagram connotes, and this extension must be again associative algebra homomorphism. So this is C algebra homomorphism. So this is what you have for this Lie algebras. Okay. So let's prove this because this is a very important result. So let's actually write down all the maps. So then you just trace the map, it will be clear. Okay, you have G, and then you have this TG, and then you have this UG. So this composition is what your iota. And note that G to TG is indeed a C-linear map. Okay. So here you have actually this A, so which is given to be unital C associative algebra. Okay, this pi is indeed Lie algebra homomorphism. Okay, so first of all, what you can say about this iota? So this iota, if you think about it, okay, so if you take some x and y here in G, okay, and then look at its image inside the tensor that will be in TG. So let's say what we are interested in. So given this xy, let's say I am interested in looking at the bracket xy. The bracket xy will lie inside T1G here. But then when you go down all the way here inside UG, this bracket xy indeed actually equal to xy minus yx. Okay, so I am dropping this tensor whenever I go to the image of the universal mapping algebra. Okay, so then it's clear that so this side which is defined, okay, so this side of the commutator which is defined inside the universal mapping algebra gives you actually kind of Lie algebra structure for this. Okay, so what I want to say, this map iota is indeed Lie homomorphism. So that's very clear. Okay. Okay, so now how we actually kind of get this extension of pi. For that, what we do, we actually take first extend this pi to TG. Okay, so first extend this to TG, and then so that this actually commutes. So indeed, what we got this pi tilde, which is a map from TG to A. So which is C algebra homomorphism, such that this map commutes. Okay. Now, in order to get map, okay, induced map from UG to A. So if you are interested in this map, okay, so then all we need to check this pi tilde, the kernel of pi tilde contains, okay, this two-sided ideal generated by x tensor y tensor x minus xy. So that means the pi tilde of this should be 0. Okay. So let's actually check. So once we check this, then we have this induced map. So from again we call it pi tilde, so that this diagram comes. Okay, maybe let's call it pi double tilde. Okay, so now it is about chasing the diagram. Okay, so the first diagram actually commutes. So this first diagram commutes and the second diagram commutes. So that will tell you that this bigger diagram will commute. Okay, that's the easy exercise. Okay, so now let's verify why we have this induced map. So if we take pi tilde of x tensor y, y tensor x minus xy, so which is just exactly equal to pi of x, pi of y minus pi of y, pi of x minus pi of xy. But note that pi is given to be Lie algebra homomorphism, so this must be 0. Okay, so that proves that x tensor y minus y tensor x minus bracket xy lies inside the kernel. So we have this induced map. Okay, as we guaranteed. So that actually proves this extension of this pi to this UG2A. But now why this is unique? Okay, there is this uniqueness as well. Okay, so this map must be unique. So this is there is this unique map like that. This extension happens and the diagram commutes, and that is because if you actually just look at the image of G inside UG, then that must generate UG. Okay, because the image of G inside TG must generate TG as associative algebra. So because UG being just a quotient of TG, the image of the successive image of G inside UG also will generate UG. Now this pi double tilde is actually uniquely determined by a restriction to the images of G. So because of that, the extension by double tilde also must be unique. Okay. Okay, that is the simple calculations. I will leave it to you. So now this indeed actually kind of gives you very important observation in terms of actually representations. So if you go to the representations, you can see that you can compare easily the representations of G with the representations of UG. So let's say we have this space of representations of G. So this is the representations of G. And then similarly, you have representations of UG. So now there is this natural one-to-one correspondence between these two. Okay, from representations of G to this representations of UG, you can define natural one-to-one correspondence. Okay. So how it is defined? So you start with representation. Okay, that means you have a map from G to GL of V. So which is a Lie algebra homomorphism. Let's call it pi. So then you have this map from G to UG, which is iota. So then this pi is uniquely actually extended so that this diagram comes. So you can take this pi and then send it to pi tilde. And this is actually unique correspondence from pi to pi tilde. So naturally this gives injective map because of the uniqueness. So now how you come back? So to come back, what you do, like if you start with the representation of UG, so if you start with the representation, let's call it so let's call it Xi, which is a representation of UG to. So now it will become map from UG to endomorphism of E. So it must be unital associative algebra map. Okay, so this Xi is indeed C algebra homomorphism. So now, given this map, what you do, like you already have this G2 UG, this iota map, and then you can simply compose. Okay, so then you actually get map from G2 endomorphism of V. But if you think about it, because G2 UG is a Lie algebra homomorphism, so this is Lie algebra homomorphism, and this is C algebra, okay, associative algebra homomorphism. So that will imply that this composition, okay, which we again call it Xi tilde, let's say that's, yeah, fine. This is indeed Lie algebra homomorphism. Okay. So now if you go from this Xi, then you just map to Xi tilde. Okay. So that actually tells you that this map is surjective. So that actually gives you one-to-one correspondence between the representations of G and the representations of UG. Now, it's not hard to see that all the notions that you actually learn about the representations of G, like irreducibility, reducibility, completely reducible, indecomposable, all those notions can be will correspond to each other, okay, under this dictionary. So that actually tells there is no difference between representations of G and representations of UG. And that doesn't actually guarantee that you can easily deal with representations of UG. But again, because of this correspondence, you can actually bring in all the tools that you have in this associative algebras to representations of G. So that approach is also well studied. For example, this book on this enveloping algebra, enveloping Lie algebra. I forgot the author. So he actually deals with this approach. So you can try to understand all possible ideals and so on inside the representations of UG, and then the associative algebra structure. Using that, if you study representation of UG, that will give you lots of information about representation of G. Okay, that's one thing. How much time I have?
You have 10 more minutes.
Okay.
10 to 12, yeah?
Yeah, okay. So I will actually state the PBW theorem, the one version. Maybe I will try to state both versions and then maybe I will stick with one of the versions and then try to prove. Okay. So we already seen that this UG is the graded algebra. Okay. So there is this grading. Sorry, not the grading. The UG is the filtered algebra. So the filtration is being images of this TMG. So recall, so pi is the map from TG to UG. So now, if you consider this filtered algebra, you can actually naturally associate graded algebra with this UG. Okay. So this is now graded associative algebra. Now, what you can say about this? Okay, so recall the grade of UG. So now this is nothing but direct sum of UMG modulo UM minus 1G, where M is from 0 to infinity. So now this graded algebra, okay, so this is one version of PBW theorem that asserts that this is indeed isomorphic to the symmetric algebra. But let's actually try to understand why, first of all, there is this natural map. Okay, so you have this graded algebra, and we want to say that there is this natural map from the symmetric algebra to the graded algebra. Okay, how one can get this map? Okay, so recall you have TG and then you have S of G, and so this is the surjection. Okay, so note that S of G is defined to be Tg modulo the ideal generated by X tensor Y, Y tensor X, where Xy varies in G. So in order to verify, there is this map from SG to grade UG. So you need to actually verify that first of all, there is a map from TG to grade UG. Okay, so that actually just follows from the following observation. So you take this natural map. Okay, so T of G is nothing but direct sum of P power mg m greater than or equal to 0. Okay, recall this is just the m tensor product. Okay, so now you have this following map from TMG to this UMG. So UMG is the image of this T small mg, which is nothing but direct sum of TKG here range from 0 to m. Okay. So then from here you have this UMG modulo UM minus 1G. So this is the natural map. Okay. And this map is indeed a surjective map. Okay, this composition. So this is surjective. So now let's use this map. So this map actually defines. So if you call, okay, let's call that map some name. Oh, sorry. So let's call this as pi m. So now this pi m that we defined from TMG to this UMG modulo U minus 1G, that is going to give you map from TG to this grade UG. Because both are graded spaces, you have map from at the graded level. Okay, this is the M graded level. So you can patch all of them and then get map from TG to grade UG. And this is again a surjective map because you have surjective map from each graded level, and then if you patch it up, you will get the surjective map from TG to grade UG. But now note that what will be like at least what elements are there in the kernel. Okay, that is easy to verify. Okay, so if you take X tensor Y minus Y tensor X, let's look at this element. Okay, so then this must be there in the kernel file. Okay, so that is because when you are looking at the images of these two inside the universal Olympic algebra, then you can easily see that. So let's look at this images X tensor Y minus Y tensor X. So which will become like, maybe I'll use this pi of X, pi of Y minus pi of Y, pi of X. So this is happening inside first the universal Olympic algebra, and then inside the universal Olympic algebra, this is exactly pi of xy. Okay, but this is degree 2 and this is degree 1. So that means this is indeed lying inside this U1. So that means inside U2 modulo U1. So this must be just 0. So this is equal to this. This is lying in U1. So this must be 0 inside U2 modulo U1. So that means, so these elements, they all lie inside the kernel. Okay, so that actually tells you that you have actually this pipe indeed factors through SG, and you have a map from SG to grade UG. Okay, so this is indeed surjective map. There is no issue, but like what PBW theorem actually asserts that this map is indeed isomorphism. Isomorphism of graded algebras. Okay. So as an immediate corollary, what you get to actually get, it is actually the version 1. So the version 2, which is what like we'll be focusing on, that if you take so the basis of this SG, the image of that should be basis inside your grade UG. Okay, so fix the basis. Let's actually work with let's work with only the finite remaining finite dimensional space. So then you can actually construct this xi1, xi2, etc., xik, like in the symmetric algebra. So you can demand that these indices are actually increasing. Okay, these I1, etc., ik, they all lie inside this 1 to n, such that this I1, etc., ik, they are increasing. Okay, so what we are doing here, like I'm actually just writing in just one line notation. Okay, so maybe let's use some different notation just to be clear. So let's write it as y, y1, y2, etc., yk. Okay, so this is indeed basis of UG. So what is yi? Yi is the image of capital Xi inside UG. So we have this map, no? So we have this map G to UG, so which we denoted by iota. So if you take Xi and then look at its image, that you call it Yi. And it's clear that Yi will generate UG. The image of G generates UG because the image of G generates TG, and UG is just a surjective quotient of TG. So Yi generates UG. And if you consider all possible words that you form from this Yi's, and you always write it in the increasing order, then you can actually say that this will form a basis of UG, because more or less that is what embedded in this isomorphism. Okay, because SG has such basis, being the symmetric algebra. So if it is isomorphic to grade UG, as C vector space, grade UG will be isomorphic to UG as a C vector space. Okay, so the grading structure will not actually disturb the vector space structure. As long as the vector space comes from UG, and grade UG will be isomorphic. So if you take the basis of grade UG, you can go to the basis of UG and vice versa. And here you have such basis. Okay, I'll stop here, and if you have any questions, you can ask. So we will actually first prove that these two versions are isomorphic, and then later actually maybe I will focus on the version 2 and then supply like proof that is available in Roger Carter.
Venkatesh, if you don't mind, just go to the chat. There are two long questions. It's better if you read instead of me reading them out for you.
Sure, yeah, sure. Can I stop sharing?
Yes.
Okay. Okay, so I am having an issue. Let's say I have n dimension space, say n greater than 4. Suppose say the pair x1, x2 commutes and the pair x3, x4 commutes, and with other commutations obtained by those two relations. This isn't object has more than one self isomorphism. Identity and map x1, x3, x2, x4. In general, we might have an issue with more this sort of product. I think universality doesn't allow us specifically say which two pair, right? Am I missing something? The issue is universal objects are unique up to a unique isomorphism. I think with partial commuting algebras are not universal. No, like, okay, partially commutative algebra, I didn't say they are universal or anything. Nah? I didn't know where this question is coming from. Can you clarify?
Sadanand,
can
you please speak?
I think you. I think that you said universal, so I thought they are universal. I think so, but
No.
think
I
you
said
they
you
are
can
universal.
actually define. So I introduced the partially commutative algebras to give some examples. Okay, so
Okay.
you can actually define algebras in between this tensor algebra and the symmetric algebra.
Yes, I get the definition, but I thought you
Oh,
said
okay.
it was
Maybe
universal.
I misspoken. I don't know. So, okay. So why I introduced them? Because you can actually define what is called this partially commutative Lie algebras with the same defining relations. Okay. So maybe I don't know whether the concept of free Lie algebras introduced. So one can define free Lie algebras. Then what you do, you take free Lie algebras, go modulo again ideal generated by the commutation relation that we are trying to impose from the graph. Okay, xi, the commutator xi xj is 0 whenever there is no edge between I and j. So then it is an exercise that if you take the universal enveloping algebra of that must be the partially commutative associative algebra that you define using the graph. So that is something you can prove just using the definition of the universal enveloping algebra, the universal property of the universal enveloping algebra.
Okay. Okay. Thank you.
So, okay, the second question. The simplicity of GLN implies simplicity of SLN. You meant only the following, or there is something more subtle? Smallest associative algebra inside GLN containing SLN is GLN itself. Yeah, okay. If B ideal of A, then associative closure. If B ideal of A, then associative closure of B is two-sided ideal of associative closure of A. I will actually dig out Heston's paper because I read it like many years back, but it is actually a natural question to ask. So you have this G, okay, let's say, which is a linear Lie algebra, which is sitting inside some GL of V. Then you can actually look at the associative algebra that is actually generated by G. So you can ask this question like how much the structure of G can be recovered from the structure of the associative algebra and vice versa. Okay, so Heston actually proves some results towards that, like only assuming something about the associative algebra, then getting something. Maybe he's actually doing it, getting both necessary and sufficient condition, modulo some, like assuming something about the ring. Okay, you should be a little bit careful about characteristic and all, because if you take SLM trace zero matrices over actually characteristic positive characteristic, then you will lose simplicity. Nah? So that is something you should be careful. So yeah, it's a long time back that I did. I would actually try to share that paper with you. Okay. So, but somehow like they are closely related. The structure of G as a Lie algebra is somewhat controlled by the structure of the associative algebra and vice versa. But there is this another question about like, so when this associative algebra generated by G will be full. Like for example, SLN if you take, so you can actually generate Mn of C, using SLN. Is that correct? As an associative algebra, yeah. And it is actually like using some kind of the arguments from density theorem. You can also try to do something very similar to that. I forgot exact statement, but you can ask this question like you start with G being linearly subalgebra, then when the associative algebra generated by that is Mn of C.
Okay.
So somewhat, because Mn of C being Mn of C is actually, that is simple algebra. So that controls a lot about what Lie algebra G could be. Yeah, we'll discuss that later. Not problem.
Okay.